Welcome everyone. Thank you for taking the time to join us for this webinar session. My name is Jobert and I will moderate today's webinar with the subject Autonomous Driving and Powertrain Electrification, two Megatrends in Automotive. First and foremost, I would like to introduce you to Sven Lamprecht, who is our speaker and subject expert. Sven joined the company back in 1996 as electroplating specialist. Then he became the global product manager for final finishes used for various assembly techniques until he was appointed in his current role as Director for Technology Exchange between OEM EMS. Sven holds several patents in the field of electrolytic and immersion plating and applications used in wet chemical PCB processing. He's a true expert in his field and we're excited to have him here with us today. So a couple of words about the webinar. The webinar will be divided into two parts. First, 45 minutes of presentation and then 10 minutes of Q&A session. I encourage you to raise questions from the beginning of Sven's presentation and therefore to use the Q&A function, which you can find on the top right corner of your screen. Your questions will be visible only to me and Sven, therefore do not hesitate to ask any questions related to the topic. We will try to cover as many questions as possible during the planned Q&A session at the end of the presentation. And if the time allows, we will answer all questions right away. Also, Sven will be available after the webinar to reach out to you via email. And last but not least, if you face any technical issues, please make sure to enter the webinar via the latest versions of Chrome or Firefox browsers. Now let me hand over to Sven and please enjoy the session.
Okay, thank you, Jobert, for the kind introduction. And let's jump into the two megatrends. First, safety and optimize the usage of lanes, which results in advanced driver assistance systems, and finally into autonomous driving and into CO2 reduction, where we focus on electrification of the drivetrain. The graph on the left shows the historical compounded annual growth rate for electronic systems used in passenger cars between 2014 and 2019. Here we see nearly 25% growth of electronics used for hybrid electrical vehicles and battery electrical vehicles, where the electronics used in advanced driver assistance systems showed an increase of close to 20%. This is for the electronics in hybrid electrical vehicles. This is nearly 20% points, or for the advanced driver assistance systems, 15% points stronger growth than the average growth of all the other automotive electronics. The growth of advanced driver assistance systems is driven by a combination of governmental and legal push and an increasing consumer demand. The graph on the right shows the targeted timeline when the different levels according to SAE, Society of Automotive Engineering, should be implemented. Anyhow, today it looks like that fully autonomous cars or robo-cars, as they are also called, won't hit the road before end of next decade. Here we see the forecast for electrified vehicles from different sources. They were collected and published by CEI Automotive. One can easily see how hard it is to forecast, especially about the future. Numbers vary between 14% and 50% market share of electrified vehicles in 2025. What is not shown here, Porsche made a similar survey with public available reports and published this at IDTechX in 2018. They averaged the year when it comes to a break-even between sold internal combustion engines and electrified vehicle. Electrified vehicles were forecasted to break even with internal combustion engines in Europe by 2038, in China in 2043, and the US should remain with a 60-40 split of internal combustion engines versus electrified vehicles until 2050. So it looks like they were much more reluctant to switch to electrified vehicles. Anyhow, we should keep in mind that CO2 reduction by electrified vehicles is strongly consumer dependent. And that's why the forecast varies so strongly. There is a strong push from the governments in Europe and China, and an additional strong push from automotive OEMs. New vehicles sold in Europe must continue to become cleaner in Europe. If not, OEMs are facing penalties if they miss the latest CO2 targets in Europe. Another reason for the uncertainty is that we're in a range of convenience. Most of the people are using nowadays MP3 players instead of CDs, using smartphone cameras, or eating in fast food restaurants. We shouldn't forget driving a battery electrical vehicle does require thinking ahead, which doesn't really fit to convenience. One has to plan his daily route to make sure you have enough fuel to easily make it back home. Coming to safety and optimized usage of lanes. So automotive safety norms are increasing. This has an impact on active and passive safety systems, as advanced driver assistance systems, for example. Here will be a growing number of these advanced driver assistance systems in this decade. This is to build up a supply chain for sensors, which is then needed for automated driving at the end. Fully autonomous vehicles, or so-called robo-taxis, will then play a much larger role in the late 2030s. These safety systems are needed for internal combustion engines as well as for electrified vehicles. So the safety systems are drivetrain independent. The graph on the right is from Bloomberg New Energy Finance, which is Bloomberg's primary research service. Here we see the COVID-19 effect forecasted for this year, and then the recovery of vehicle sales over the next years. Additionally, we see, at least what they forecast, there will be a maximum of 100 million vehicles sold per year. And these are all candidates for active and passive safety systems. Here we see the average semiconductor content by level of automation, from level 2 up to level 5, where level 2 equipped cars will have an adder of around $150 of semiconductor. Level 3 cars will add $580 of semiconductor, and level 4 and 5 cars will add roughly $860 of new semiconductors. The semiconductors shown here are further broken down into camera modules, radar modules, LiDAR modules, sensor fusion, and actuators. Taking the example of radar systems, the semiconductor content will grow from $90 in a level 2 car up to $230 in a level 4 or 5 car. And as a semiconductor without a PCB is just a paperweight, the amount of PCBs has to increase as well. And as PCBs without connectors are also just a paperweight, we need to add more connectors to the overall system too. Other strong growing areas used in all levels of automation are camera modules, first within the cabin to monitor the driver to see what he's doing, as he will still be responsible for driving the car, and external cameras for color and object identification. LiDAR modules will also show a strong growth rate, and electronics for sensor fusion. Here we see a forecast from Yole, how the different levels of automation are penetrating into new passenger cars. On a worldwide base, there should be roughly 6 million level 2 cars sold this year. This number should grow to more than 20 million sold level 2 cars by 2030. In 2030, there should be a total of roughly 33 million new cars with level 2 to level 5 capability. Taking the semiconductor content from the previous slide, level 2 cars was $150 of new semiconductors, level 3 cars was $580, and level 4 and 5 cars was $860. One can easily calculate the growing number of semiconductor value. This will increase from nearly $1 billion this year to roughly $10 billion in 2030. So next to the semiconductor amount, the amount of PCBs and connectors will increase as well. As mentioned earlier, this is independent of the drivetrain. It's a combination of governmental and legal push and an increasing consumer demand. Here we see the systems needed to enable the different levels of automated driving or advanced driver assistance systems to enable those different functions. In the top box, we see the different functions for level 2, level 3, and level 4 and 5. To name a few, there are functions as emergency braking, lane keeping assistant, cruising chauffeur, or automated parking. As mentioned on the slide before, on a worldwide basis, there should be roughly 6 million level 2 capable cars sold within this year. And this number will grow to more than 20 million level 2 cars by 2030. In 2030, we will see roughly a total of 33 million cars sold with level 2 to level 5 capability. Taking the numbers of systems required to enable a level 2 capable car, there are 13 systems required. These include cameras, short and long range radars, surround and rear view cameras, and an ADCU, an advanced automated driving control unit. The number of systems required for a level 3 capable car will increase to 21 systems, adding LiDAR, and finally to 27 systems for a level 4 of level 5 capable car. With the number of level 2 to level 5 capable cars, the amount of systems required will jump from roughly 80 million systems in this year to more than 500 million systems in 2030, where radar and camera systems are the largest portion of all systems being used. Coming to CO2 reduction with focus on electrification of the drivetrain. The long-term outlook for electrified vehicles remain bright. Fundamental costs and technology improvements outweigh the impacts of COVID-19. Even if right now some electrified car model launches are delayed, car manufacturers are still sticking to their long-term commitments. On the right-hand side, we see again a graph from Bloomberg for global traveled distance by drivetrain. So the majority of traveled distance remains with internal combustion engines. By 2030, electrified vehicles will only contribute to roughly 10% of all kilometers being driven. So compared to a battery electrical vehicle, engine downsizing, more hybrid cars, and more lightweight materials are more likely to happen to reduce CO2 emissions. We see on this slide the breakdown of semiconductor content by the different levels of electrification. A car with an internal combustion engine has roughly $355 worth of semiconductors to run the engine. To add to this car a 48-volt system, this will add another $100 of semiconductor. The 48-volt system is typically used for mild hybrids or for a boost function. Hybrid vehicles add an average of $340 to the $355 needed for an internal combustion engine. So the semiconductor value is nearly doubled when we add the electrical drivetrain to the internal combustion engine. And a battery electrical vehicle requires nearly $700 worth of new semiconductor content. When nearly half of it comes from power management, which is used in chargers, inverters, converters, and in the battery management system. Taking the green bar at the center of those graphs, those are the power semiconductors. So the power semiconductor content will grow from $75 for a 48-volt system to $380 for a battery electrical vehicle. This is the strongest growing segment for the semiconductors. Here we see a forecast from Boston Consulting Group, how the different levels of electrification are penetrating the drivetrain. What is expected up to the year 2025, everything what's happening is driven by regulations. After that, it will start to be consumer driven, the growth of more electrified vehicles. The color codes, what we see here, green and brown are diesel and gasoline engines. All the other colors are different levels of electrification. On a worldwide basis, there should be roughly 7 million electrified cars sold this year. So anything from 48 volts to a battery electrical vehicle. And this number should grow to more than 50 million sold electrified cars by 2030 on a worldwide basis. Taking the semiconductor value from previous slide, cars equipped with a 48 volt systems are adding $100. Plug-in hybrids are adding $340, and battery electrical vehicles are requiring close to $700 of new semiconductor. With these numbers, we can easily see and calculate the growing semiconductor value. So the semiconductor value will increase from a little bit over $2 billion this year to $19 billion in 2030. Now let's come to the key trends and requirements resulting out of these two megatrends. Looking at the key drivers for future technologies needed for automotive electronics. The first obvious driver is cooling and thermal management. This is mentioned nearly everywhere. All technologies are affected, from components to modules to PCBs and the connectors as well. The other critical driver is electromagnetic shielding. Electromagnetic radiation comes from, for example, charging the battery at high voltage, like 1000 volt with high amps, like 400 amps, or while driving, when you consume all that electricity again. The generated electromagnetic field should not harm the passenger or interfere with safety relevant devices in the car. Cost, as always, is the next driver, as we'll add more semiconductor, PCB, and connectors to the car, so there will be a huge pressure on all those individual items. And last but not least, reliability. More to cost and reliability on the next slide. So here we have it. Reliability and cost. Typical systems and modules designed needed for advanced driver systems and to further electrify the drivetrain don't exist as needed. And that's what we should always keep in mind. They don't serve either reliability or cost requirements for automotive needs. As an example, just put your cell phone in the car during winter time, it will not work. But you expect the car radio to work, which is built on a different technology. As another example, cameras and displays are produced by billions for smartphones and tablets. This would fit the cost requirements what automotive is expecting. Unfortunately, they are designed to last a maximum of 3 years in a temperature range between 0 degrees C and 40 degrees C. So firstly, cars should at least 10 to 15 years and not up to 3 years as consumer products. And secondly, the temperature range for cars is dramatically different. And nobody wants to spend money on replacing all the cameras after a few years or rely on those cameras during summer or winter time when those cameras are being used outside of the specified temperature range. Devices designed for consumer applications are under-tested, under-designed, and therefore at risk under automotive stress loads. On the other hand, there would be systems or modules matching the reliability requirements for automotive. Those are from military applications, for example, radar, GPS, or navigation systems. Unfortunately, they're much too expensive, heavyweight, and bulky to be placed into the car. And to summarize, they are over-tested, over-designed, and therefore too costly for cars. So this dilemma creates the need for new technologies to serve cost and reliability requirements from automotive. What is not shown here, but essential for advanced driver systems up to robo-taxis, we need to add computing power to the car, a lot of it. Looking at the 27 systems in a level 4 car or level 5 car, all that data collected needs to be crunched and the right decisions need to be executed. All that software to do this needs to be run fast and decisions need to be done in milliseconds. Well, there are fast computers available in data centers and they last many, many years, but they're a bit bulky, run at constant temperatures, and are not exposed to automotive loads like vibration, shock, and so on. This will impact the design of computing power for cars in future too. The effect of higher voltage when we're charging up to 1,000 volts, for example. So higher voltage is needed, for example, to charge the batteries of battery electrical vehicles to get enough kilowatt hours in a short time frame. To increase the kilowatts for charging, either the voltage or the amps need to be increased. With the higher amps, or to increase the amps for getting more kilowatts, have a downturn that cables and conductors need to be thicker, which adds weight. So the increase in kilowatts by voltage is a way out, which does not add additional weight to the modules. This will result, on the other hand, in issues like CAF, conductive anodic filaments. And this especially when moisture and ionic contamination are present. Dendritic copper growth between the solder resist and the dielectric will occur. This will at the end create shorts. On the right-hand side, we can see some images showing the dendritic copper growth. The top image shows copper dendrites growing on top of the solder resist. The image below shows dendrites on top of the dielectric underneath the solder resist. So it grows within the dielectrics. And the one on the bottom shows a dendrite which grows through the solder resist at the corner of the conductor where the solder resist is thinnest. One way out are stronger hydrophobic dielectrics and solder resists to exclude moisture or water uptake. The other is to eliminate ionic contamination, as both are the culprits in this case. Higher voltage, another focus area will be the surface finish. With higher voltage and thus with a wider potential range between conductors, corrosion resistance of surface finishes will get more important. As an example, taking silver as a surface finish, moisture and high voltage will create strong dendritic growth. Surface finishes enabling high corrosion resistance or high phosphor ENIC or immersion tin, and both are promising candidates to survive with moisture and ionic contamination in this kind of environment. If wire bonding is required, then electrolysis palladium, autocatalytic gold, or nickel palladium gold are good choices also to survive. So on the next slide, the effects of higher temperature. As a rule of thumb, every 10 degrees C temperature increase, the failure rate doubles. And this is really not what we want, and especially not in automotive. So to eliminate hotspots on our components and to shrink the BGA footprint on a PCB, VPO, via and pad plated over, is creating now more and more attention, so the soldering pads can be placed directly under those hotspots. Typically, the through vias are conformal copper plated, then epoxy filled, grinded, and plated over again. That's where the name comes from. A technology being used for packaged substrates since many years is copper through via filling. So we're filling the through vias completely with copper. And this technology is being tested today for PCBs to further improve heat dissipation under hotspots. Copper through via filling got an attention also for PCBs, as it shows a 2.7 times faster heat transfer rate compared to epoxy-filled vias. And at the same time, the electrical resistance drops by 20%. Another effect on IMC formation by long-time thermal exposure or current-induced electromigration within solder joints is also well understood. This result will impact reliability, as both the high temperature or current-induced electromigration within solder joints will create more intermetallic compounds, and this will make the solder joints more brittle. So choices for surface finishes will be narrowed down to anything with nickel underneath or between the copper and the solder alloy. So either again a high phosphor nickel gold or a nickel palladium gold. Both show higher resistance towards intermetallic compound growth than typical surface finishes where copper tin IMCs are formed, as example with OSP. Another focus is due to reduce the tendency of warpage, especially when PCBs are being heated during usage and then cool down during idle times. Based on the CTE mismatch of the different materials used, components and the solder joints are heavily exposed to mechanical stress. An example what high temperature over a long time period can do to copper conductors is shown on the image on the right-hand side. The investigation was performed by the National Physical Laboratory in the UK. They exposed PCBs with ENIG up to 3,000 hours at 250 degrees C. After 3,000 hours, only the ENIG layer survived. The copper conductor oxidized completely. Oxygen diffused through the dielectric. At the dielectric to copper interface, the copper layer started to oxidize until all copper was gone and only the cap of ENIG survived. The effect of higher frequencies. Well, it's well understood that PCB properties change when a PCB is heated, both properties, electrical and mechanical. And the heat can be produced within a PCB as an artifact of high-frequency analog or high-speed digital signal processing. For high frequency or high speed, decay and DF are critical, and both change when temperature changes. For DC, this was not so important, but for higher frequency, this is getting critical. So thermal management is getting important. Thermal management of microwave components, circuits, or systems is simply a matter of removing the heat or trying to avoid to produce heat in the first place. Most of our RF components, circuits, and systems suffer damage or performance degradation from heat. One way out is to minimize loss by using lower decay or DF dielectrics, as the loss otherwise generates heat. Those low loss decay DF dielectrics are more costly than standard FR4 materials. So those dielectrics are only being used on those layers where high-speed signals are being processed. This leads to hybrid buildups. One layer might be PTFE containing, whereas the other layers are FR4 for cost reasons. This challenges any kind of desmear, as a compromise between the different materials need to be identified to desmear the PTFE containing or FR4 layers. Another way out to minimize loss is to focus on smoother conductor surfaces, where the target surface roughness can be as low as 15 to 30% of the skin depth. There is not only a focus on the interface copper to dielectric, but also at the interface dielectric to copper, so the bottom of the conductor. And this is especially for microstrip configurations. We see more than half of the loss is due to the roughness of the copper foil. Another focus area is the capability of a surface finish for corrosion protection, as not always all areas are covered by solder resist. For example, with radar, the antennas, or exposed thermal vias or thermal pads. If the surface finish corrodes or oxidizes over time, the electrical properties will change accordingly. And where the surface finish is, that's where the skin is, and that's where the signal travels. Stable and robust surface finishes are immersion tin, as after reflows, tin will be transferred completely into to copper tin IMC, which is a kind of bronze, and this is stable. So this composition will not change anymore, and is one of the best corrosion protections available. Another surface finish is palladium gold surface from electroless palladium and autocatalytic gold. This combination is pore-free and doesn't attack the copper layer in comparison to palladium layers with an immersion gold process on top. With an electroless palladium autocatalytic gold layer, the copper structures are protected from the environment. Both metals are precious enough not to get corroded, and they won't diffuse or mix with the copper layer. So that sandwich layer of palladium gold is stable over time and doesn't change. When not directly plated onto the solder resist, plated shielding layers become also more important, especially for components and modules. Dies and chips move closer and interfere by electromagnetic radiation. At frequencies below 100 megahertz, sputtering and ink spraying will not work anymore. They are much too thin to be effective, and uniformity for three-dimensional structures is not given, especially the sidewalls of components. So thick metal plating is needed. This can be done by electroplating. So electroplated copper and electroplated soft magnetic layers will help for shielding. And this combination is proven to effectively shield neighboring dies on the same substrate or module. So coming to the last slide, what does that all mean for us? Well, at the first bullet point, we see an increase of IOs. This is to support several advanced driver assistance systems and their functions. We also see more embedded devices. For performance and reliability reasons, embedding chips will drive the need for higher aspect microvias, and on the long run will face up to 5 HDI layers within automotive, which could get a reliability concern with stacked microvias, which is a topic of several investigations and publications nowadays. At the second bullet point, higher integration in denser PCB designs, so electromagnetic shielding layers are necessary to avoid emission and ensure immunity. Just think of inverter, converter, and batteries. All of them are running at kilowatts, whereas antennas are running at milliwatts. The third bullet point, multi-source stresses in an automotive environment. We need new designs for devices that exist already today. As mentioned earlier, nobody wants to rely on designs for smartphones used in an automotive environment. Here we need robust designs dealing with multi-source stresses, for example, mechanical stress, power, and temperature induced, and all at once. At the fourth bullet point, to safety not only cast, we'll see hybrid PCB builds. Not only FR4 with PTFE will be used, as an example in radar applications. We'll also see more rigid flex to avoid connectors or to utilize limited space in a car. This could be also just a single side flex, like bend to fit kind of stuff. At the last bullet point, for thermal management and power delivery, there is a wide field, from insulated metal substrates using lightweight aluminum, for example, or the need for thicker copper layers. But there is a risk that too much copper will add weight, and this could be sometimes too much weight. As an example, just adding 400 microns thick copper layer within the PCB will add roughly 3.5 kg per square meter of weight, and this will be a lot for automotive. And in general, there's the need for better heat transfer. And for example, what I mentioned is by copper through via filling. Another one, conductive anodic filaments will become more prone due to materials capable to handle high voltage or high TG. And those materials are typically more brittle. So there's a high risk with conductive anodic filaments. And the last one, warpage control. And here we especially have to deal with several different materials which have different CTEs in one PCB buildup. And this will create a lot of stress if PCBs are being heated up during normal use and then cooled down during idle times. There will always be a lot of stress onto the solder joints for the components. And that's what we also have to keep an eye on and make sure the stress is not getting too high. Okay, thank you. That was the presentation part.
All right, thank you very much, Sven. It is time to proceed with the Q&A session. We received a few questions, so I'd like to remind you that we'll cover as many questions as possible during the session, and all the rest will be answered by Sven after the webinar via email. So let's start. The first question we have is, what is the maximum aspect ratio for through-hole filling?
Okay, so for void-free through-via filling, we tested it up to 1.2 millimeter. And this was done in a horizontal tool with a iron redox system and pulse reverse rectification. We also tried vertical with DC plating, but here you always end up with a huge void at the center of the via, which entraps liquids, and then during reflow, this can do popcorning. So with pulse reverse plating and the iron redox system, this allows for void-free filling and a minimum copper thickness on the surface, also with a low dimple. Okay.
All right, then the next question we have is, what is the benefit of plating versus spray coating for electromagnetic shielding?
Okay, so spray coating typically uses precious metal, which has a cost effect. And metals are typically like nano-sized silver, or also in combination silver with carbon nanotubes, which are also quite costly to achieve a certain conductivity. So spray coating is in competition more with sputtering, not plating. Plating is a key enabler, for example, for the low frequency near field shielding, as metal layers are not limited in thickness by electroplating, or you can easily combine different metals or alloys. So plating is more replacing the bulky metal lids with space or footprint on a PCB is precious, and it also helps on weight reduction, which is always a topic for automotive. Additionally, the direct plated metal on a resin of the molding resin of a component also acts as a heat spreader compared to paint, which is more of an insulating layer on the component. Okay.
All right. There is another question related to that. Is there a need for a special adhesion promoter for plating on molding resins?
Yeah, well, molding resins are a bit differently built up than normal PCBs or FR4 or the epoxies used in PCBs. And this has to do with some waxy components inside. So the adhesion promoter first has to start to de-wax those molding resins. And then you need because also the composition is slightly different, you will end up to need also a special adhesion promoter, just focusing on the molding resins. Typically PTH or electrolysis processes from PCB manufacturing will not work.
All right. Then we have another one here. What are the main contributors for dendrites on the PCB surface?
Okay, I think this has to do with the high voltage. The image is what I show. So there are three things you need to create dendrites with copper. So it's voltage, moisture, and ionic contamination. So if we eliminate one of them, then we're fine. So to eliminate voltage doesn't make too much sense. So we have to focus on moisture uptake of the dielectric and on the surface of the dielectric. And we have to focus on ionic contamination. And those two will be the focus areas in future. So we're going to see more hydrophobic solder resists, and we have to make sure there are no ionic contaminations left on the solder mask.
Okay. Then there's another question on, I believe it's slide 18. There is a higher resistance to IMC growth mentioned. And the question is why?
Okay. Well, typically, if we create more intermetallic compound, our solder joints will get more brittle. And there are two mechanisms to drive intermetallic growth. One is a well-known isothermal exposure, which lets the tin continuously react with the metal from the solder pad, especially if you just have copper underneath. And the other reaction is based on current flow through the solder joint. And this is called also electromigration. And based on the electron flow, the tin from the soldering alloy will also continue to react with the metal from the solder pad. And as there is a difference in resistance to form IMC, so if you solder on copper or on nickel, the IMC thickness will be different. And this is in favor for nickel, and even there, more in favor for high phosphor ENIG or nickel palladium gold. As both surface finishes slow down the intermetallic formation. Or don't show
all right, then
soldering directly on copper.
Gotcha. Okay. Then there is another question, and at some point, I think you mentioned the need for more stacked microvias, and the question is, what's the reason behind seeing more stacked microvias rather than staggered microvias?
Okay, more stacked microvias, yeah. So one example is the increased need for computing power for the high levels of automation of cars. So if we look then to level 3, level 4, and level 5 advanced driver systems. So to deal with the computing power which is needed for those levels of higher levels of cars, the BGAs used will show an increased number of IOs, so the density increases. And to reroute all those IOs, we need to deal with more microvias to enable this. And as space is limited, we're going to see more stacked microvias compared to staggered microvias. And that will make the or the reliability of microvias a much stronger topic than it was in the past for automotive.
Yeah, and I think we have a separate webinar for all those who are interested in that you can access through the Autotech website on microvia reliability. There's another question related to the shielding, and the question is, can the shielding by plating be applied on PCB too?
Yes, the shielding layers can be copper is anyway valid, but also the the soft magnetic layer, they can be applied within the PCB or on the solder resist itself.
Okay. And let's see, another question here. Let's see. On page, I believe it's page number 4, you mentioned the forecast for electrified drivetrains, and the question is, why does it vary so much?
I assume, put it this way, that some of those forecasts are a little bit too optimistic or too pessimistic. And I think that's why Porsche did that survey where they averaged the year when there will be a 50-50 split between internal combustion engines and electrified vehicles. And also one reason could be that maybe the really optimistic ones were created during a hype, and maybe the other ones were created by petrol heads. So it all depends on whom you interview for a survey. So it will look different if you do a survey in Europe or if you do a survey in Asia or in the US. I think that's where the huge variation comes from.
Thank you. Then I think the last question, and I don't see any other ones in the Q&A session there. The question is about palladium, and the question is, up to what temperature range is palladium an effective copper diffusion barrier?
So we did once for automotive storage test, and we tested up to 500 hours at, I think it was 150 degrees C. And the results were confirmed by Auger measurements. So it was like a 50 nanometer thick palladium layer topped by 50 nanometer autocatalytic gold. And even after 500 hours, we could not see that any copper diffused up to the surface. What we did see that a small portion of palladium and gold diffused into each other, but no copper moved to the surface. So it's a pretty good diffusion barrier for copper.
Okay, and I think that was the last question we had. So we are wrapping up a little bit early, but thank you everyone for your attendance and your attention. We really appreciate you being here. After we close the webinar, you'll receive the replay link for this webinar. And if you liked it, feel free to share a link of the recording, which will be available to view after you register. For the upcoming and on-demand webinars, you can visit www.autotech.com/media/webinars. We'll also keep you updated about our webinar schedule via email. Stay healthy and safe, everyone, and see you the next time. Thank you very much.